well, and you've read the email that I sent out to all of you. If you haven't read that, just go ahead and stop this. Read that first. That's very important. It tells you exactly when each week different things are going to be due, such as, for example, on Tuesdays, always there's going to be a quiz, 45 minutes at most in length. Um, and every Thursdays, you're going to have discussion questions due, and then every Monday, you're going to have to respond to some people's discussion questions in much shorter responses. Again, read that email if you haven't already. Otherwise, let's go ahead and get started on the Earth's atmosphere. You will probably hear cats in the background. That's the nature of the beast here. Yep, there he goes. Okay, that's Sophie. Uh, so we're going to talk about the composition of the atmosphere, the origin of the atmosphere as kind of our first week. We'll probably talk a little bit about, as this says, clouds and precipitation. Maybe if we get time later on. More importantly, I want to talk about the origin, the composition of the atmosphere. Then we're going to talk about climate and weather. And then if we, as part of weather, we'll talk about clouds and precipitation. So just going through your slideshow. Since people are chatting in the Discord, I'm stopping. I'm not going to record that audio. Air has long been known to exist as something separate from just kind of vacuum, right? Maybe back in ye olden past, people thought that air was really nothingness, that it was a void. But as early as the ancient Greeks, it was kind of assumed, since wind can move things and since it can cool things down, air was some kind of substance. And as a substance, it was assumed to be one of the fundamental elements of the universe. But since then, we've come to understand that it's actually a very specific mixture, of course, of different gases. This mixture originated kind of recently, right? So the nitrogen and oxygen atmosphere we have nowadays has not always been Earth's atmosphere. It's not the only kind of atmosphere a planet can have. Early on, we had a lot of helium. You can probably guess why helium gas was very prevalent. It's very common in stars. Same with hydrogen. It's also very light. So when we had that outgassing of the gases trapped within the planet as it started to melt and kind of settle, the lighter gases emitted first, right? They floated the fastest, basically, and they emitted out into the atmosphere. Eventually, over time, they floated away from the planet just because Earth isn't big enough to have enough gravity to trap those gases on that little thin layer of atmosphere around it. There was also methane, just another very light gas, right? That has about the mass of a single oxygen atom, so it's half the density of oxygen gas, right? Methane is. And ammonia, really nitrogen in general, as we see, nitrogen makes up most of the atmosphere these days. Nitrogen in general, it doesn't really stay in rock very easily. It's very easily dissolved, especially when you have water, as we ended up having the later atmospheres and more recent atmospheres. That nitrogen, basically, because it's so easily dissolved, think of it as very soluble in water. Different kinds of nitrates are very soluble. So there's not a lot of nitrogen in the rock, even though eventually all of that dissolved nitrogen ended up becoming nitrogen gas in the atmosphere. So over time, we got more nitrogen. We also got more oxygen, and we know how that happened. We've already talked about how that occurred because of early life, early photosynthetic life. It's not really plant life. We wouldn't say plants, but definitely photosynthetic organisms, basically saying if we're going to build ourselves and create energetic molecules with carbons, we can take that carbon from carbonate rocks and from CO2, and there's a lot of excess oxygen in that process that gets turned into oxygen gas. As this says, oxygen was not from the early volcanic outgassing. This happened over time. We talked about this in the early first quarter, I think, where the oxygen was created by early living things undergoing photosynthesis. These living things were cyanobacteria, kind of early bacteria, in these large kind of built-up structures that were made of both rock and organic material, stromatolites. This right here is an early photosynthetic reaction. Nowadays, this is a more complicated molecule, glucose, that has more carbons, hydrogens, and oxygens. C6H12O6. As I said, air is a specific mixture. It is not just any old gas, right? As the Greeks thought of air just being a gas of any kind, that is not the scientific definition of air. The scientific definition of air is talking about the gas in Earth's atmosphere, especially at sea level, right? It is that very specific nitrogen, oxygen, argon, water, etc. mixture that we're going to talk about in this slideshow, and you're going to be researching on your own in the book. It also has a lot of solid particles, things like dust flecks, maybe volcanic ash, right? Salt in the air, soil particles if you're down close to the ground. Water, both in the form of liquid water and solid water, of course, ice. And then attached to especially these solid particles, certain kinds of microorganisms, and then spores that are airborne, usually not attached to solid particles. Pollen. Spores are, I believe they are already fertilized genetic material, if my biology is correct, and I might be wrong about that. Pollen is definitely only, it's basically plant sperm mixed with some kind of agents that make it float through the air more easily. So biological agents, some entire organisms, some fertilized reproductive cells, and some unfertilized reproductive cells, all in the air. Here, this is going to be pretty important, especially for the first couple here, for you to know. The composition of Earth's air. It is close to 80% or 78%-ish nitrogen, 20 to 21%-ish oxygen. So if an alien came down and was looking at Earth's atmosphere, they'd probably say this was a nitrogen atmosphere that the living things have polluted with oxygen, right? This is a totally, or all of this oxygen was basically released by living things over Earth's history. There's also, depending on humidity, excuse me, I am a little under the weather. Good thing I'm staying home, right? There's going to be some amount of water in the atmosphere depending on humidity. This can range from basically zero, perfectly dry environment, to a extremely humid environment. If it's very hot, then it can hold a lot of that water, and it can hold up to 4% in normal climatic conditions in the tropical regions, which is a huge amount of water if we think about the amount of mass that the atmosphere represents. Argon, a noble gas, not very reactive as a result, if you remember from IPS, just around 1%. Everything else is basically trace. We have neon and helium, other noble gases. We have carbon dioxide. Of course, this is relevant because it is increasing in the atmosphere by just small amounts, which we will talk all about in climate. Methane, another greenhouse gas, way down here in the, let's see, this digit would be the 1/1000th. So that's the 1/1 millionth. So in the 1 part per million range for methane. And then these other gases, nitrous oxide, important for the formation of acid rain, for example. Ozone, very important for both the formation of smog at ground level and in the ozone layer that I'm sure you all have heard of. All these gases are very, very dilute compared to carbon dioxide, even let alone argon, all the way up through nitrogen. And as this says, over recent time, this is fairly constant. So even though the atmosphere has changed quite a bit in Earth's history, Earth's kind of now at this stable point where everything's a little bit stationary and not changing very quickly, with the exception, of course, of anthropogenic changes in carbon dioxide and methane, anthropogenic meaning human-caused, and nitrous oxide and tropospheric or low-level ozone, as well as water changing with weather and temperature. But nitrogen, oxygen, argon, and kind of the overall averages of these things from year to year, again, with the notable exception of the gases that humans are releasing, pretty constant these days. As it says, these gases humans are affecting, and water varies with the weather. Water, of course, is in the air as water vapor, but also as liquid water and solid ice particles. Let's see, do we have... Oh, yeah, okay. We will talk about condensation nuclei when we talk about cloud formation and weather. You can get a head start looking at that if you want. Carbon dioxide, of course, released by respiration of living things, and of course also when we burn fossil fuels of any kind, that carbon in the hydrocarbons is released as carbon dioxide. And that has been increasing quite rapidly, as this shows, over about the past 150 years. Notably, that is, if you remember your history, around the time of the Industrial Revolution, when, wow, people were burning more coal. And by looking at studies, although this graph only goes out to 1750, studies actually that go back out thousands, tens of thousands, sometimes even hundreds of thousands of years show that to be very remarkably consistent until that last 150 years where there's been that spike. And this is somebody taking data that would go back tens of thousands of years in the form of ice cores. Basically, this is Mohole Man's, I don't know, grandmother, grandfather. They're bundled up. Who knows? Ozone is an important gas we will talk about. Basically, ozone absorbs, the reason we care about the ozone layer is because it absorbs ultraviolet light. Ultraviolet light basically can cause cancer in the skin by damaging DNA. Notably, ozone absorbs ultraviolet light both in its formation and its destruction. So here in the ozone layer, where most of the ozone exists, oxygen absorbs some amount of UV light to break apart and form ozone, O3 instead of O2. And then that more unstable ozone absorbs other UV light to break apart again into O2 and oxygen that can form back into O2 or another O3 molecule. Basically, the formation of, the amount of UV light that gets through that ozone layer is decreased both by the oxygen just being there and the ozone being there. So that ozone layer does a great benefit to us as far as removing that UV light from solar radiation by the time it reaches the surface. It also leads to the heating up of the stratosphere, which we'll get to when we talk about the layers of the atmosphere. Because of various kinds of pollution, there's also a buildup of ozone at ground level. Unlike the ozone in the stratosphere that protects us from UV light, that's not really doing a lot more to protect us, and it's actually harming us actively because that ozone, O3, it is very unstable, and it likes to react with all kinds of different things. So it can react with your tissues, especially in your lungs, and basically cause cancers on its own, or uh, it can react with metals in buildings and rust those buildings or damage them in other ways. Uh, it also can just fog up and make travel very difficult just because of how dense that fog can become when there's a lot of ozone in an area. So it's really uh, not a great thing to have down at surface level, and it is the major component of smog. There is a cat that's about to turn on a Roomba. All right, move, son. Excuse me. All right, and you all have probably heard about the hole in the ozone layer from the 90s. That while it's starting to recover after these CFCs, chlorofluorocarbons, were reduced by an international agreement called the Montreal Protocol. Excuse me, Montreal Protocol. These CFCs are really damaging. Basically, uh, the chlorine part of the chlorofluorocarbons starts to react with the oxygen and basically breaks down ozone and keeps it, kind of pushes everything towards this just oxygen side of things. And worst case, or excuse me, not worst case, but what's worse, I should say, is those chlorine atoms, singlet chlorine, not chlorine gas, Cl2, but Cl1, will basically keep cycling through this. They don't bond and then kind of get stored away as chlorate or something like that. They just keep cycling through as chlorine atoms until they meet another chlorine and turn into chlorine gas. So that reaction happens on average hundreds of thousands of times before the chlorine is neutralized. So one chlorine atom has a huge effect on reducing the amount of ozone if it makes it to the ozone layer. And so for that reason, it was highly disruptive and destructive to the ozone layer. And Earth scientists kind of spread the warning about this, that this was going to increase the amount of damaging radiation that would reach us at the surface. And in a case that seems impossible nowadays with the way that politics is going, people listened, they thought that was alarming, and they enacted change in order to reduce that. And now the ozone layer is starting to recover from that damage. We've already talked about the atmospheric particles. You can look at this on the slideshow yourself. This is an example of just a dust storm in Australia that covered, a large part of the continent. And let me quickly see. We will start with the layers of the atmosphere in the next lecture.